In this session, let us solve some questions from exercise 1.3, which is of long answer type. First question is show that square of any positive integer is either of the form 4q or 4q plus 1 for some integer q. Solution: apply Euclid's division lemma for a and b equal to 4 such that there exist unique m and r satisfying a is equal to 4m plus r, where 0 less than or equal to r less than 4. Therefore, possible values for r will be 0, 1, 2 and 3. If r value is 0, then a becomes 4m. Squaring on both the sides, we get a square equal to 4m whole square, nothing but 16m square. So a square can be written as 4 times of 4m square, which is 4q form, where q is equal to 4 times m square. Let us take the value of r as 1. Then a becomes 4m plus 1. Now squaring on both the sides, a square will be equal to 4m plus 1 whole square. Let us expand this 4m plus 1 whole square. It becomes 16m square plus 8m plus 1. In the first two terms, I can take 4 as common. I will be getting 4m square plus 2m added to 1, which is something like 4q plus 1, where q is equal to 4m square plus 2m. Let me continue this part. If r is equal to 2, then a becomes 4m plus 2. Now by squaring on both the sides, a square will be equal to 4m plus 2 whole square. Expand the right hand side, we get 16m square plus 16m plus 4. Now in the three terms, 4 is common, so 4 times 4m square plus 4m plus 1, which is like 4q form, where q is equal to 4m square plus 4m plus 1. Last part, if r is 3, then a will be 4m plus 3. Now by squaring on both the sides, a square becomes 4m plus 3 whole square. If we expand it, we will be getting 16 16m square plus 24m plus 9. The same can be written as 16m square plus 24m. I'll write 9 as 8 plus 1 so that in the first three terms I can take 4 as common. I'll be getting 4m square plus, if 4 is taken common from 24, we get 6m plus 2, then added to 1, which is like 4 cube plus 1 form, where q is equal to 4m square plus 6m plus 2 for some integer. Therefore, we observe either they become 4q form, where remainder is 0 and 2, or it becomes 4q plus 1 when remainder is 1 and 3. Therefore, square of any positive integer is either of the form 4q or 4q plus 1 for some integer q. Let us solve the second question. Show that the cube of any positive integer is of the form 4m, 4m plus 1 or 4m plus 3, 4m, 4m plus 1, 4m plus 3 for some integer m. If you observe in the previous question we had something like 4q plus 1, so we had considered m and r. Let us now take r, and instead of m we will take q. Solution: apply Euclid's division lemma for a and b equal to 4. Such that there exist unique q and r satisfying a is equal to 4q plus r, where 0 less than or equal to r less than 4. Therefore, the possible values of r will be 0, 1, 2 and 3. If the value of r is 0, then a becomes 4q. In the question they have asked cube of any positive integer, so we need to cube on both the sides. It becomes a cube equal to 4q whole cube. This becomes 4 times of 16q cube, which is like 4m form, where m is 16 times of q cube. If the value of r is 1, then a becomes 4q plus 1, cube on both the side, we get a cube as 4q plus 1 whole cube. On expanding this 4q plus 1 whole cube, we will be getting 64q cube plus 48q square plus 12q plus 1. I take 4 common out of the first 3 terms, I'll be getting 16q cube plus 12q square plus 3 cube, then added to 1, which is like 4m plus 1 form. Now let us take the value of r as 2, then a will be equal to 4 cube plus 2, cube on both the side. A cube will be equal to 4 cube plus 2 whole cube. Expand 4 cube plus 2 whole cube. We will be getting 64 q cube plus 96 q square plus 48 q plus 8. We can take 4 common in all the terms. I'll be getting 16 q cube plus, if 4 is taken common in 96, I'll be getting 24 q square plus 4 taken common in 48, I'll be getting 12 q. 4 taken common in 8, I'll be getting 2. So it is like 4m form. Now r value, if you take it as 3, then a will be equal to 4 cube plus 3. Cubing on both the sides, we get a cube equal to 4 cube plus 3 whole cube. Expand this 4 cube plus 3 whole cube, we get 64 q cube plus 144 cube square plus 108 cube plus 27. Now let us take the same expression. I will slightly change this by writing 27 as 24 added to 3. The reason is, in the first 4 terms, I can take 4 as common. I'll be getting 16 q cube plus 36 q square plus 27 q plus 6, then added to 3. So it is like 4m plus 3 form, where m value is 16 q cube plus 36 q square plus 27 q plus 6, where m is some integer. We have observed that either it becomes 4m form when r value is 0 as well as 2, it becomes 4m form, or it becomes 4m plus 1 form for r is equal to 1, 4m plus 3 form for r is equal to 3. Let us solve question 3. In the question 3, we are asked to show that square of any positive integer, very important, cannot be of the form 4 cube plus 2, 4 cube plus 3 for some integer q. We shall solve the question using the same previous method. Apply Euclid's division lemma. For a and b equal to 5. Since they have asked 5q plus 2, 5q plus 3, so I am taking value of b as 5. such that there exist in this question I am taking M and R satisfying A is equal to Pm plus R. In this case, it is 5m plus R, where 0 less than or equal to R less than 5. In the previous two questions, it was less than 4. So the possible values were 0, 1, 2, 3. Now there is one more added. Possible values for R will be 0, 1, 2, 3 and 4. So we need to find it for R equal to 0, 1, 2, 3 and 4 also. If the value of R is 0, then A becomes 5m. Now if we square on both the sides, squaring on both sides, we get A square is equal to 5m whole square, which is 5 times of 5m square, say 5q form. If R is equal to 1, then A will be equal to 5m plus 1 whole square. Let me take this as a second step. A square will be equal to 5m plus 1 whole square. This implies A square is 25m square plus 10m plus 1. I can take 5 as common in the first two terms. It becomes 5m square plus 2m added to 1, which is 5q plus 1 form. If R value is 2, then let me again take the second step itself. A square is 5m plus 2 whole square. Further expand, we will be getting A square equal to 25m square plus 10m plus 20m plus 4. 5 common in the first two terms. I get 5 times of 5m square plus 4m, then added to 4, like 4q plus 4 form. If the value of R is taken 3, then the square, A square becomes 5m plus 3 whole square. On expansion, A square will be equal to 25m square plus 30m plus 9. This 9 I'll write as 5 plus 4. So it is 25m square plus 30m plus 5 plus 4. In the first three terms, 5 taken common, I'll be getting 5m square plus 6m plus 1 added to 4. Nothing but 5q plus 4 form. If the value of R is taken 4, then A square will be 5m plus 4 whole square. Therefore, A square will be equal to 25m square plus 40m plus 60. Like the previous step, I will be writing this 16 as the multiple of 5, that is 15 plus 1, so that 5 is taken common in the first three terms. I'll be getting 5 times of 5m plus 8m, so 5m square plus 8m plus 3 added to 1, which is like 5q plus 1 form, where q is some positive integer. Observe in this question, we have to show that it cannot be of the form 5q plus 2 or 5q plus 3. Observe the forms obtained here. They are 5q, 5q plus 4, 5q plus 4 and 5q plus 1. Therefore, square of positive integer cannot be of the form 5q plus 2 or 5q plus 3, because we are getting 5q, 5q plus 4 and 5q plus 1 form. Hope you have understood the previous question, where we have shown that it cannot be of the form 5q plus 2 or 5q plus 4. Same way, here we need to express using Euclid's division lemma and show that positive integer square cannot be of the form 6m plus 2 or 6m plus 5 for some integer m. If you have understood the previous question, you will be able to show this square of any positive integer cannot be of the form 6m plus 2 and 6m plus 5 easily. Hope you will try this. If you try, you must be getting squares. When r is say 0, a square will become like 6m form. For r equal to 0. For r equal to 1, square of the number a square will be of the form 6m plus 1. When r value is 2, then the square of the number will be of the form 6m plus 4. If the value of r is 3, then the square is of the form 6m plus 3. If the value of r is 4, square of the number is of the form 6m plus 4. If the value of r is taken 5, square of the number is of the form 6m plus 1. Finally, you can conclude it is not of the form, cannot be of the form 6m plus 2 or 6m plus 5. Will you try this? What you need to do is, you have to consider the value of b to be 6, such that there exist m and r satisfying a is equal to 6m plus r. Will you try this? Yeah, it's easy. You can try this. Let us look at question 5. Show that square of any odd integer. Very important question. Square of any odd integer is of the form 4q plus 1 for some integer q. This is very important question. It is asked in the examination several number of times. Let us solve this. Let's apply Euclid's division lemma. For a and b value as 4, such that there exist unique m and r satisfying a is equal to 4m plus r, where 0 less than or equal to r less than 4. So the possible values of r 0, 1, 2 and 3. If r is 0, then a is 4 times m. If r is 1, then a is 4m plus 1. If r is 2, then a is 4m plus 2. If r is 3, then a is 4m plus 3. I have written this so that we will be able to identify which one of these are odd and which one of these are even. Look at the first one. R is equal to 0, then a is 4m, which is a multiple of 2, so it is even. This one is 1 added to even, so it is odd. Here 2 can be taken common in this, so it becomes 2 times of 2m plus 1, which is even. This is 1 more than the previous one, so it is odd. In the question, we need to take square of any odd integer. So I have to rule out this even one and I have to consider these odd ones. So I'll take r as 1, then a is 4m plus 1, square on both the sides. Square on both sides implies a square is equal to 4m plus 1 whole square. Now squaring on both the sides, I'll be getting 16m square plus 8m plus 1. In the first two terms, I can take 4 common. I'll be getting 4 times m square plus 2m plus 1. So this is something like 4q plus 1 form. In the same way, when r is 3, we have odd number. So if r is equal to 3, a is equal to 4m plus 3, square on both the sides, square on both sides. This implies a square is 4m plus 3 whole square. Expand it, we get a square as 16m square plus 24m plus 9. Like the previous questions, I change this 9 as 8 plus 1 so that in the first 3 terms I can take 4 common. So 4 taken common, I'll be getting 4m square plus 6m plus 2, then added to 1. So a square is 4 cube plus 1 form, where m is some positive integer. So by observing, you will be able to say that the square of any odd positive integer is of the form 4 cube plus 1, so some integer q. One more important question, question number 6. If n is an odd integer, then show that n square minus 1 is divisible by 8. This question we had solved it in exercise 1.1. If you remember, look at question 3 of 1.1. We had explained how an odd integer, when it is squared and 1 is subtracted from that, is divisible by 8. Now kindly solve this. Refer exercise 1.1 question 3. Try it out. It is also an important question. Question 7. It is little logical. Prove that if x and y both odd positive integers, then x square plus y square is even but not divisible by 4. Very important thing to note is they both are odd positive integers. So let me take the value of x as a odd number form, say something like 2m plus 1, and the value of y as something like 2n plus 1. We know these both are odd formats, 2m plus 1 and 2n plus 1. Now as per the question, I need to do this x square plus y square. So I need to expand this 2m plus 1 whole square added to 2n plus 1 whole square. Expand it, I'll be getting 4m square plus 4m plus 1 plus 4n square plus 4n plus 1. Further, I'll write this as 4m square plus 4m, 4n square plus 4n plus 1 added to 1 becomes 2. Here I can take 2 as common. I'll be getting 2 multiplied to 2m square plus 2m plus 2n square plus 2n plus 1. Observe, it's very clear that 2 is multiplied to these terms. What does it mean? It means that it is even. Further observe, it is 2 multiplied to some number, not 4 multiplied to the number. This number is, therefore, x square plus y square is even and not divisible by 4. Next question. Use Euclid's division algorithm to find highest common factor of 441, 567 and 693. In class 6, you have done similar type of question using division method, if you remember. What did we do? We had found highest common factor of two numbers. Then we had taken the result with the remaining number and we have found the highest common factor. Let's recall that. Let me take these two numbers. Let me use 6 standard method, division method, and try to find the highest common factor. 567 one time is 567 and it leaves the remainder 126. Since remainder is not 0, I have to divide the previous divisor using this remainder. 126 4 times is 504 and I get 63 as a remainder. Now I need to divide this 126. 2 times is 126. So the remainder is 0. It means the highest common factor of these two numbers 567 and 693 is 63. Now take this result 63 and try dividing this remaining 441. Clearly 63 7 times is 441 leaves remainder 0. It means that the highest common factor of these three numbers 441, 567 and 693 is 63. That was very easy. Now you need to solve the same question using Euclid's lemma. It's not a very difficult task. Let's use division lemma. Apply Euclid's division algorithm. Euclid's division algorithm. To 567 and 693. We have divided at this part. You can refer to that and write this 693 larger number as 567 multiplied to 1 and remainder 126. It's there in this division step, first step. In this case, r is not 0, so I need to continue further and express this 567 as 126 multiplied 4 and the remainder was 63. Now 126 is written as 63 2 times and the remainder is 0. It means the highest common factor of 567 and 693 is 63. Now let me write it here. Now apply Euclid's division lemma to 63 and 441. So this 441 is written as 63 times 7 plus 0. Here r is equal to 0, which implies 63 is highest common factor. Let me write the result here. Highest common factor of 441, 567 and 693 is 63. It's very easy. I have taken here 567 and 693 in the beginning. You can consider any two of these three numbers. The same procedure is followed and the same result will be obtained. One more important question. Prove that root 3 plus root 5 is irrational. To prove, let me consider root 3 plus root 5 as a rational number. Say root 3 plus root 5 equal to p by q, where p and q are integers and q not equal to 0. Let's square on both the sides. We get 3 plus 5 plus 2 root 15, which is equal to p square by q square. I'll retain this 2 plus root 15 towards left hand side, and the sum 3 plus 5, which is 8, I'll transpose it to right hand side. Further, on simplification, I get root 15 as p square by q square minus 8 divided by 2. Look at the left hand side. Left hand side is root 15 and it is irrational number. Look at the right hand side. Right hand side is p square by q square, which is a rational, minus 8, again rational, and this divided by 2, which is also a rational. At this step, we have irrational number, which is left hand side, equal to rational number, which is right hand side. This is wrong. This contradicts. Our assumption. Therefore, it cannot be a rational number, which means root 3 plus root 5 is irrational. Next question. Show that 12 raised to the power n cannot end with the digit 0 or 5 for any natural number n. Look at this 12 raised to the power n. If I express this as a product of prime, it is 2 square multiplied to 3 raised to the power n. It is like 2 raised to the power 2n and 3 raised to the power n. You know that for a number to end in 0, the required factor are 2 and 5, and for a number to end with 5, the required factor is 5. This is not possible. In this question. Therefore, 12 raised to the power n cannot end in 0 or 5 for any natural number n. Now we shall solve the last question of the exercise, that is question 12. On a morning walk, three persons step off together and their steps measure 40 centimeter, 42 centimeter and 45 centimeter respectively. What is the minimum distance each should walk so that each can cover the same distance in complete steps? We have come across this type of question in class 6th. Here, the required distance will be the LCM, the least common multiple of 40, 42 and 45. We shall find this least common multiple using fundamental theorem of arithmetic, that is prime factorization method. 40 is nothing but 8 multiplied 5 times, it is 2 cubed into 5. 42 nothing but 6 7 times, nothing but 3 into 2 into 3 multiplied to 7. 45 is 9 5 times, so it is 3 square into 5. So the least common multiple will be 2 cube into 3 square into 5 into 7. All the numbers expressed in prime product should be considered along with their highest power. Here the highest power of 2 is 3 in this. You can observe it is highest power is 3. Here you can observe the highest power is 2 and 5 the highest power is 1 and 7 is having the power 1. So the least common multiple is 2520. When you multiply we get 2520. Therefore required distance is 25.2 centimeter.